video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises.
By now, we're all comfortable with the seismic wave as a bang, generated near the surface, propagating downwards, and reflected back. In this module, we ask for a clearer view. What bang? What actually happens to a little piece of rock as the wave passes through? And how does that depend on the geological nature of the rock? And then the intensely practical questions. What limits does all this impose on what we can reveal with seismics? And how can we push back those limits?
We start with an earth material that is uniform, solid. No layers, no grains, no pores, almost like a metal. Sitting, let us say, on a rigid, immovable basement. Then slowly, gradually, we apply a uniform downward pressure. To visualize it, let's say an infinite array of weights on the surface. Now, what happens?
Well, the material becomes squeezed. Any representative cube of the material suffers two effects. It changes volume, and it changes shape. These changes are resisted by an internal property of the material that the man in the street would probably want to call stiffness.
Okay, now, instead of that steady state situation, let's hang all the weights from sky hooks, touching the ground, but not exerting any pressure, until we cut the ropes. The weights are as before, and in the end, everything else must be as before. An even distribution of the particles with the same degree of squeeze. But before that steady state is reached, what happens?
First, of course, that sudden downward pressure displaces and compresses the particles near the surface. At this stage, the compression is not against the immovable basement, because the surface does not yet know that the basement is there. It is just against the inertia of the particles.
So that in this transient situation, the behavior of the particles is controlled not only by the stiffness of the material, representing the reluctance of the particles to be forced closer together, but also by its density, representing the reluctance of the particles to be accelerated.
So the downward displacement of the surface particles causes a compression of the particles below, which is relieved in part by their motion. This in turn causes compression of those below and their motion. The boundary between the compressed zone and the undisturbed zone is, of course, a seismic wavefront, a plane seismic wave. As it propagates at seismic velocity, it progressively causes deeper and deeper particles to move, and so extends the compressed zone.
As this wavefront strikes the rigid basement, it can no longer cause motion, because we have said that the basement is immovable. We shall look at this situation in detail in GP203. For the moment, let's just say that the wavefront is reflected back to the surface.
During the upward path, the surface, which still does not yet know that the basement is there, continues to move down. Again, and again.
Thereafter, there are some ups and downs that we shall postpone to GP203. But let's be sure to take these points. The motion of the particles is independent of the basement, until the seismic reflection gets back with a message that the basement is there. Until that time, the transient, that is, the seismic behavior, is governed by both stiffness and density. After that time, the system progressively settles down to the steady state, controlled by stiffness alone.
Now, instead of that step of pressure applied at the surface, let's drop the weights. As they bounce, we'll catch them on the skyhooks, so that we get one quick, clean impulse of pressure, a spike of pressure. Now what happens?
First and foremost, we know that an elastic material springs back to its original position after the pressure is removed. In other words, a spike of pressure must give a spike of displacement, at least.
All right. So let's look at the situation a few milliseconds after the drop. By then, a particle in the surface has been displaced and has returned to its original position. A particle down here has not yet been reached by the wave, so it also is in its original position. A particle here is at its maximum displacement, to here. Ahead of that, a particle has not yet moved so much. Behind, here is a particle moving back after its maximum displacement. So if we graph the particle displacement as a function of distance, we get this.
Now let's look at the degree of compression of the particles. In the undisturbed zone, of course, uniform spacing of particles. But here at the front, the particles are spaced more closely, while here at the tail, they are further apart. So that if we graph the degree of particle compression, we get this. Positive compression, where the particles are closer than normal, and negative compression, that is, rarefaction, where they are further apart.
With, of course, zero mean, so that there is no compression left in the material after the wave has passed.
So these pictures give a snapshot of the whole material at one instant of time. But in practice, we usually couple a detector to the material and record what comes out as the wave passes across it. 1 point in space as a function of all time. The form of the curves is the same. Particle displacement as a function of time. Degree of particle compression likewise.
Let's just say displacement and excess pressure. Excess because we are concerned only with the seismic pressure, not the static overburden pressure.
There's another variable we might measure, the velocity with which the particles are moving. From GP201, we know this must be the slope of the displacement curve. The differential of particle displacement is particle velocity.
From which we can see that in a plane wave, the graph of particle velocity has the same form as that of excess pressure.
Which is physically clear here, where the displacement is changing fastest. That is, the peak of particle velocity is where the particles are most closely bunched together, the peak of excess pressure.
As it happens, the most convenient measurements to make in seismics are particle velocity with a geophone and excess pressure with a hydrophone. So we are happy to see that particle velocity and excess pressure are in phase in a plane wave.
For a plane wave, then, we need a source of infinite dimensions, here illustrated by an infinite weight dropped on a hard material. A clean single bounce, say giving a clean downwards displacement, down and up. For these conditions, everything is over in a few milliseconds, so we can call this a spike of displacement. And so a spike doublet of particle velocity and a spike doublet of excess pressure. All very simple.
Here's another delightfully simple feature. In a lossless material, a plane wave propagates onward with no change of amplitude and no change of form. There is no decay of amplitude, no change of shape forever. Very simple indeed.
Now let's ask how the measurements we usually make, particle velocity and excess pressure, how they depend on the nature of the material. And let's start to move toward real rocks.
Okay. Well, we've said that the two important properties of the material are its stiffness, which is the reluctance of the rock to be squeezed, and its density, which is its reluctance to be set in motion. So the particles in a dense, stiff rock are hard to get going. We say it has a large seismic resistance.
Or a large acoustic impedance. That's the usual term.
In seismics, the acoustic impedance is a very important property of the rocks, and we need to be totally comfortable with it. Granite, a very large acoustic impedance. Soft clay, a very small acoustic impedance.
There's an analog here with the flow of water in a pipe. From a certain water pressure, we get large water motion if the resistance of the pipe is small, and small water motion if the resistance is large. So in the seismic case, a certain excess pressure produces a lot of particle motion in a rock of small impedance, but only a little in a rock of large impedance.
In a seismic wave, as we have agreed, the initial compression makes the particles move, and the particle motion in turn creates a compression. We can say that, as in all wave motion, there is a continual interchange between potential energy, represented here by the excess pressure, and kinetic energy, represented by particle motion. So that a wave of a certain energy in a young clay has small excess pressure, but large particle velocity, while a wave of the same energy in a granite has large excess pressure, but small particle velocity.
So two fundamental properties of a rock to us are the density and the stiffness. These become mingled in the acoustic impedance. They are also mingled in the seismic wave velocity. So rearranging, we have that the acoustic impedance is the product of density and seismic velocity.
Right. Although this is perhaps a less fundamental definition of acoustic impedance, this is the one we all carry in our heads. As we say, rho v.
Now let's keep crystal clear in our minds the distinction between particle velocity, the speed at which the particles are moving, and seismic velocity, the speed at which the wave is moving.
We saw an illustration earlier. The seismic wave gets all the way down and back, while the particles in the surface are moving only from here to here. The wave velocity is ordinarily much larger than the particle velocity.
But it's not just a matter of magnitude. It's a difference of nature. Particle velocity is a measure of the amplitude of the wave, not of its speed.
For example, the speed of the impact, that's the particle velocity. Small speed, small impact, small amplitude. Larger speed, larger impact, larger amplitude. But the speed of the impulse through the line of spheres, that's the wave velocity, independent of the amplitude.
Now, how do these fundamental seismic properties, density, stiffness, velocity, any two will do, how do they depend on the nature of the rock?
Let's look first at the clays and shales, fine-grained, perhaps deposited in deeper water, far from shore, and renowned for being very compactable.
So there are no surprises. At the sea floor, more than half the volume is water. Deeper, under the weight of the overburden, the grains are forced closer together. The porosity is decreased, with the excess of water squeezed back up into the sea. This process goes on until at greater depth, the rock becomes almost solid. So graphically, we can plot the decreasing porosity with depth, or, what is much the same thing, the increasing density with depth. At great depth, almost the density of the grains themselves, say 2.6. At the sea floor, a comparable mix of water and grains, say 1.8. And in between, a more or less smooth curve, often smooth enough to be represented by an equation.
So the density of shales is very simple, very well behaved. We can even say that since most geologic successions are dominated by shales, we can expect a density depth curve quite like this one almost everywhere. However, there is one circumstance that can change this dramatically. If it happens that the shale succession is interrupted by an impermeable layer, salt for example, then the water in the pores below can no longer be squeezed out back into the sea. It is trapped in the pores, and so resists their closing. The water is now contributing to the support of the overburden. It is overpressured, holding the grains apart. The density is therefore anomalously low in an overpressured zone.
Now about velocity. Again, no surprises. The velocity increases as the shale compacts. Indeed, we can often do surprisingly well with this same curve. The one curve serves for both density and velocity.
However, this apparent duplication should not hoax us into thinking that velocity is as simple as density. Density is almost completely defined by porosity. Velocity is not.
To get the physical picture, let's first look at salt, cubic crystals, almost like the material we started with. Elastic compression involves a change of volume, and just that change of shape, from square to rectangle. In particular, there is no sideways deformation. This cube would like to bulge sideways, but it cannot because of the ones beside it trying to do the same. So salt, limited to this simple behavior, is, for an earth material, very well behaved. A consistent density of about 2.1 and a consistent velocity of about 4,400 meters per second. both increasing only slightly with depth.
Now, let's look at a porous sandstone. Initially, we take an idealized one with spherical grains, in this cubic packing. The porosity is 40-odd%, and the density is totally determined by that, a little less than 2. But the stiffness, and hence the velocity, is not so easy, because now the grains can bulge sideways into the pore space.
So now the velocity must depend, first, as before, on the reluctance of the grain material to change volume. Second, to a greater degree than before, on the reluctance of the grain material to change shape. Third, a new item, on the reluctance of the pore fluid to change volume.
That's because the outwards bulging of the grain is resisted by the fluid.
And fourth, on the number and type of the grain contacts, where any bulging of the grain is inhibited.
To illustrate that last point, we can note that this cubic packing of spheres has just 6 contacts per grain, but it is an inefficient packing and unstable. In most real situations, it would soon flip to this more efficient packing, with a porosity of 26%, a density of 2.2, and 12 contacts per grain. Now, on any one grain, there are in 3D twice as many places where bulging is inhibited. Therefore, the balance of importance between the first 3 factors is changed. The velocity now depends more on the grain's resistance to change of volume, less on the resistance to change of shape, and less on the saturant.
And the effect of depth? Well, obviously this packing of spheres is already extremely strong. There is little compaction, and so only a slight increase of velocity with depth.
Now, those spheres may be a fair approximation to a dune sandstone, with the grains well-rounded and well sorted by the desert wind. But a near-shore sandstone may be quite different. The grains, not yet rounded, may be very irregular and scarcely sorted at all. And the grain contacts are likely to be angular, a few of them bearing most of the stress, others scarcely touching. Some grains with several grain contacts, others with only a few, yet others scarcely confined at all.
The stiffness of this sandstone soon after deposition, and hence its velocity, must be small. The grains have a large surface area unsupported by grain contacts, and so great freedom to bulge sideways. But as the grains are buried deeper, the weight of overburden forces a more efficient packing. The number and area of the grain contacts increase. The possibilities for bulging decrease. The stiffness increases markedly, and so does the velocity.
And that's not all. As mineral-rich waters are expressed from the deeper rocks upwards through the sandstone, cements are precipitated around the grain contacts. Those that formerly were near misses become strong cemented contacts. Those that formerly resisted bulging over only a small area now resist it over a larger area.
So that quite a small amount of cement, an amount that would not make very much difference to the porosity, can cause a dramatic increase in velocity.
But once this cement is in place and the sandstone is consolidated, it becomes more and more like the dune sandstone. And further changes in velocity follow quite closely the changes in porosity.
Indeed, in this situation, the consolidated sandstone, typically of porosity 20% or less, we find a clear relation between porosity and velocity. If this is a unit cube of the porous sandstone, and we visualize moving all the solid material to the left, the fluid saturant to the right, so that this distance is the porosity, then the relation says that the time for a seismic wave to cross the porous block from left to right is the same as the time to cross first the solid material and then the fluid.
We call this relation the time average equation. It is a very useful relation between porosity and velocity for consolidated granular rocks with liquid in the pores.
Good. Let's summarize then the distinctions between the velocity behavior of sandstones and that of shales. With clays and shales, there is a well-behaved relation between density, porosity, velocity, and depth. The mechanism for this depth dependence is simple compaction. The compaction of deformable grains with the attendant loss of porosity.
There are some variations on this simple picture. First, the densities and velocities are reduced in any overpressured zone where the overpressured saturant is holding the grains apart. Second, the densities and velocities are likely to be increased in any uplifted zone, once buried deeper than it is at present.
And third, the interrelation of grains is different if the grains tend to be flat. Then, in general, the surface area of the grains is more constrained by grain contacts vertically than horizontally, less chance to bulge vertically. So it is often observed in laminar shales that the velocity parallel to the bedding planes exceeds the velocity perpendicular to the bedding planes by 10, 20, even 25%. These shales, then, are anisotropic in velocity.
All right, now to the sandstones. Here the depth dependence of velocity and density is much less systematic. In part, this is because of the greater depositional variability of sandstones. A cemented sandstone of poor porosity may occur shallow in the section, whereas an unconsolidated sandstone of good porosity may occur deep. Then, in part, it is because the changes in density and velocity are not primarily due to compaction. The grains themselves are stronger, less subject to static deformation. And in part, it is because so much depends on local factors: the angularity of the grains, the sorting of the grains, the chemistry and temperature of the pore waters, and such factors as pressure solution and recrystallization at the grain contacts.
Oh, enough of that. Let's just pull out two facts that are of paramount importance to the search for oil and gas in sandstones. First, although it is safe to say that if a shale and a sandstone have the same porosity at the same depth, then it is the sandstone that has the higher velocity. The interesting case, obviously, requires that it is the sandstone, the reservoir, which has significantly greater porosity. Then there may be no velocity distinction between the porous sandstone reservoir and the surrounding non-porous shale. This, of course, is bad news. We can detect the reservoir seismically only if there is some distinction, some contrast of seismic properties. Second, and here is better news, the velocity of a porous sandstone reservoir can depend quite significantly on the saturant.
Yes, but only in any situation where the grains are free to bulge sideways, to deform into the pore space.
That is, particularly in angular sands without much cementation, not so much in well-rounded, highly cemented sands.
Then if the grains can deform into the pore space, how much they do so depends on the resistance offered by the saturant, and in particular, whether it is liquid or gas.
We shall have great fun with this in later modules, for obviously it offers us direct seismic detection of gas. But that's for another day.
We have agreed that in all rocks the density is rigorously related to the porosity, and that in some rocks under some conditions the velocity may also be related to the porosity. This suggests that we look for a direct relation between density and velocity. Empirically, it seems sound to relate velocity to the fourth power of density, what we call the Gardner relation.
Thus, if we plot a large number of observations on shales worldwide, we get a result like this, with logarithmic scales to show up any power law relation. And there it is, velocity given by about 100 times density to the fourth, over a surprisingly wide range of velocity.
For sandstones of porosity less than about 20%, the fourth power is the same, but the multiplier is about 120. But at larger porosities, we see a change. The unconsolidated sandstones stay more or less on the line, but well-consolidated sandstones have higher velocities. This zone, therefore, represents the effect of the degree of cementation.
There are quite similar effects for limestones and dolomites, so that if we need a coarse approximation for all rocks, we can use this simple relation.
It fails for gypsum and anhydrite, and of course it fails totally for salt. But for most common rocks it does surprisingly well.
Always provided that the rocks are normally pressured. Overpressure, we remember, changes everything. Not only does it act to hold the grains apart, and so reduce the significance of the grain contacts, but the attendant lack of moving waters inhibits cementation. Overpressured velocities are always significantly low.
So we cannot escape from the fact that the velocity of rocks is a complicated variable. The geologist wants us to measure these variables. But seismically, it is not easy to do more than measure velocity and perhaps indirectly density, and so indirectly stiffness. Unfortunately, there is no one-to-one relationship between what we can measure and what we are asked to measure. So in future modules, we shall be working like beavers to get the utmost geological information out of velocity.
Like beavers. But right now, we should talk about another seismic property of the rocks, absorption. Earlier we said that in a lossless material, a plane wave goes on forever, with no change of amplitude and no change of form. And obviously, that does not ring true. The real Earth is not a lossless material. A plane wave in the real Earth progressively loses its high frequencies by absorption, and so decays in amplitude and changes in form. We do not know as much as we would like about the mechanism of this loss, nor how it relates to the geological nature of the rock. But there are some things we can say.
For any particular rock, it does seem that there is so much loss per cycle of the vibration, or, if we prefer, per wavelength of the path.
For example, the loss might be 0.2 dB per wavelength, or say 2% per wavelength. Then at the high frequencies with many wavelengths and a given path length, each cycle would still be 2% smaller than the last. Overall, a large loss. At the low frequencies with few wavelengths and the same path length, each cycle still 2% smaller than the last, but overall only a small loss.
So if we plot the absorption loss as a function of frequency for a given path length, we obtain a clear high-cut filter, slight for a path length of 1 second, significant for 3 seconds, serious for 5 seconds, which is, of course, what we see on real seismic records.
Or the same thing in the time domain. For a spike of displacement at 0 time, we would get a slight loss and slight broadening at 1 second, significant at 3 seconds, serious at 5.
Think of thunder. A sharp crack if it's up close, a dull rumble if it's far away.
Although the most meaningful way to express absorption is as so many dB per wavelength, sometimes we also use Q. Loosely, we think of Q as rock quality. Perhaps 1,000, small absorption, deep in the section, 100, medium absorption, shallow in the section, and 10, large absorption, in the near surface.
Absorption, then, is a confounded nuisance. It progressively destroys the bandwidth and crispness of our seismic pulse, and so limits the attainable resolution. Further, although large absorption obviously ties in some way to low velocity, we do not yet know how to use absorption to extract more geology, even if we could measure it accurately, which we cannot. It is all a confounded nuisance.
Let's leave plane waves now and talk about spherical waves. Since we do not have infinite sources, the only waves we can actually generate in practice are from sources small relative to a wavelength, spherical waves.
In the present context, all the practical seismic sources have common features, and so we shall take just one as an illustration. The traditional explosive charge we remember from GP301. So, bang! In a fraction of a millisecond, the solid explosive becomes hot gas at high pressure. Usually, this pressure is more than the rock can withstand. The material is cracked, crushed, pulverized, and permanently compressed. The ultimate nonlinearity. This blows a hole, a real cavity, perhaps a meter or so across. Even beyond that, the propagation is still nonlinear. We say supersonic, meaning that the particle velocity exceeds the wave velocity. The wave is a shock wave. Of course, this wave decays in amplitude as it spreads out, and so we can visualize a sphere at which the amplitude falls to a level where the propagation becomes linear. We call this sphere the equivalent cavity. It is usually much larger than the real cavity. Perhaps it is several meters across. Beyond this, the propagation is linear, and we can use all the simplifications that go with linear processes. The wave is no longer a shock wave, but a linear elastic wave.
Then we can regard the equivalent cavity as our effective source of spherical waves. So what is different from plane waves?
First, Since the energy in the wave is now being distributed over a wider and wider area, the amplitude must decrease with distance. In contradistinction to a plane wave, the amplitude of a spherical wave decays inversely with distance.
This is a big effect. Relative to the amplitude at 0.1 second, for example, the amplitude is down to 1/2 at 0.2, 1/4 at 0.4, 1/10 at 1 second, and 1/50th, just 2%, at 5 seconds. We call this decay spherical spreading.
Second, for a plane wave, we said that one clean bounce of the infinite weight would give us a spike of applied pressure, which would generate a propagating spike of particle displacement. But if we visualize a spherical source, with a spike of pressure supplied along this radius, for example, there is also a spike of pressure applied here, in the opposite direction. These then cause outward displacements, which in turn create a zone of rarefaction between them, so that every outgoing compression is followed by rarefaction, every positive spike of displacement by a negative spike of displacement. So whereas with a plane impulsive source the material just springs back, with a spherical source it is also pulled back.
Now, that second negative spike. We remember from GP201 that the addition of that negative spike represents differentiation, whose response in the frequency domain is 0 at 0 frequency, then rising proportional to frequency. The unwelcome conclusion from this, then, is that it is difficult to generate low frequencies from a small source.
This, of course, is why a good hi-fi system always has or simulates large loudspeakers. Big bass notes come from big sources.
Now all that, we remember, was for a spike of input pressure. But an explosion does not generate a spike. The hot gases maintain the pressure for a time, so that the gross effect is more like a step of pressure. Therefore, integrating the doublet, we get a spike of particle displacement. Or, differentiating again to get what we would actually measure with a geophone, a spike doublet of particle velocity. And therefore, this same spectrum, falling at the low frequencies.
But if the equivalent cavity were to be larger, the two spikes would be farther apart. The particle velocity is now no longer a simple spike doublet, the differentiation operator, but this,
which changes the frequency spectrum. Instead of the spike doublet, with its rather weak frequency spectrum, rich only in the very high frequencies, the larger cavity yields this spectrum. Still 0 at 0 frequency, but distinctly richer in all frequencies within the seismic band, and particularly the lows.
So there's an important conclusion. Anything that makes the equivalent cavity small gives us a weak high-frequency pulse, while anything that makes it large strengthens the pulse at most or all seismic frequencies, and particularly at the lows.
As a first illustration, let's consider a typical charge, at typical depth, in a typical shooting material, yielding a typical equivalent cavity. Its effective output, the geophone signal we receive some distance away, might be this. Basically, our spiked doublet, with perhaps a tail from further oscillation of the cavity. Now we ask, what happens if we increase the charge? Well, the equivalent cavity is bigger, of course. The actual pressure level at the equivalent cavity, depending only on the shooting material, is the same. But the surface area of the cavity is larger. In particular, the output is larger at low frequencies.
Now, let's put the original charge deeper, where the shooting material is more compacted, stronger. At the equivalent cavity, the pressure level is now larger, but the surface area is smaller. The balance of these opposing factors usually makes the pulse weaker. It is always higher in frequency.
The same effect if the geology changes and we are shooting in a harder material at the original depth.
While if we shoot in a weak and highly nonlinear material, up in the weathered zone, for example, we get the low frequencies that go with a large cavity, but at very small amplitude.
These pulses, then, represent the effective output of the spherical source. We call them source signatures. Very loosely, we can think of this first peak as being the explosion itself, this first trough as the differentiation inherent in a spherical source, and any further wiggles as the settling down of the cavity as a damped resonant system.
This source signature, then, the effective output from the spherical source, becomes the effective input to the Earth. The amplitude of the pulse we observe at distance, therefore, depends on the placement and size of the charge, and on the decay imposed by spherical spreading. The shape of the pulse we observe at distance depends again on the placement and size of the charge, and on the high-cut filter imposed by absorption. For example, if this absorption is imposed on a source signature having this spectrum, the final pulse spectrum is this, a typical seismic pulse spectrum. The low-frequency cut is imposed mostly by the differentiation in a spherical source. The high-frequency cut is imposed in part by the size of the equivalent cavity and in part by absorption. These are the three major agents forming the reflection pulse.
All of this puts a heavy burden on the geophysicist responsible for a land dynamite crew. It is he who decides what size charge, how deep, in what shooting material, and thereby decides the source signature. To do this intelligently, he must understand the exploration objective. Is it deep penetration, or shallow resolution, or what? Thus, if the objective is deep, chances are he will call for large charges in holes of medium depth, preferably shooting in clay. But if the objective is shallow resolution, he is likely to be shooting deeper or in harder material. This is something that can be decided only empirically, with a proper understanding of the needs and the expectations. It is a real responsibility.
Let's look at some of the other consequences of using spherical waves. The wave front is a spherical shell of compression and rarefaction. Any ray, locally perpendicular to the wavefront, is a radius. The ray gives the local direction of propagation of the wave energy. It is also the direction of motion of the particles.
The ray that is perpendicular to the layering goes through the interfaces without change of direction. But those that are not perpendicular are bent at each interface by the process of refraction.
The amount by which a ray is bent is given by Snell's law. If we measure the angle of incidence and the angle of refraction, then the ratio of their signs is the ratio of the velocities.
Refraction is a very important process in seismics. We need Snell's law all the time, so we have to memorize it. Oh, notice, by the way, that it involves only the velocities, not the impedances, just the velocities.
Three features of refraction are particularly interesting. First, from Snell's law, if the far material has the higher velocity, the ray is bent toward the interface, and the reverse. Second, if the far material again has the higher velocity, there is an angle of incidence that causes the refracted ray to graze the interface. This special angle, which is very important, is called the critical angle. There is no special counterpart when the velocities are reversed. And third, to get a ray from a point A in the near material to a point B in the far material, there is only one possible ray path.
Intriguingly, this one path represents the least possible time between the 2 points. Fermat's principle of least time. If we can swim at speed v and run at speed 4v, then the fastest route from A to B is the one for which the sine of this angle is 1/4 the sine of this angle. It is not the shortest route, but it is the fastest route, and rays take the fastest route.
Snell's law is the basis of the refraction method, by which we can find the depth of a particular high-velocity layer buried below a low-velocity layer. The ray that strikes at the critical angle is refracted along the interface in the deeper material at the high velocity. The local particle compression in the wave causes the interface to bulge. This bulge travels along the interface at that high velocity. Then the bulge generates a compressional wave in the upper material, which can then be detected at the surface. A long array angled to give the least time from source to geophone.
Then the difference in time from one geophone to another gives the refractor velocity. and the depth of the refractor then follows from the geometry of the ray.
This is a powerful method, particularly for studying the near-surface layering, and we shall return to it in later modules.
More generally, Snell's law is the basis of ray tracing. For any stack of layers of given thickness and velocity, Snell's law defines the unique least-time ray path from the source to a particular geophone. Looking at this ray, for example, we can see that all the layers increase in velocity with depth, except this one. The bending is in the opposite direction in this low-velocity layer.
Yes, the fastest path covers more distance in the high-velocity layers, less distance in the slow layers. Overall, the path length is greater than the direct path, the unrealizable direct path, but the time taken is less.
What happens if the Earth is not layered like this, but substantially all featureless shale, with the type of velocity-depth relation we considered earlier? By representing it as a succession of very thin layers, subject to Snell's law at each interface, we can compute a ray for any chosen entry angle. Indeed, the rays for each of a range of entry angles.
Then points of equal time along these rays must define a wave front. So for any given velocity-depth relation, we can compute the corresponding wavefront chart, giving the rays for a range of entry angles, and the wave fronts for a range of one-way travel times.
A case that is particularly helpful for visualizing these curved rays occurs when the observed velocity-depth relation can be adequately approximated by a linear relation. Then it happens that each ray becomes circular, about a center at this level, eventually returning to the surface without help from reflection. Further, even though the velocity is increasing downward, the wavefronts remain spherical, but about a center that drifts downward with time.
Such delightful simplicity. Rays circular about a center up in the air, wavefronts spherical about a center slowly falling. That's the kind of simple picture that lodges easily in the mind. Here's another useful concept that endears itself to us by its simplicity: Huygens principle.
According to this, any point on a propagating wavefront, whether plane, spherical, or any other, can be regarded as the center of a spherical Huygens wavelet. So we can take a number of sample points on such a wavefront and construct a spherical Huygens wavelet on each of them. Then the position of the wavefront a short time later is the envelope of these little Huygens wavelets.
We do have to accept that there are some problems with Huygens' principle. Let's say it does not give the whole picture. But it is remarkably good at telling us how a wave gets from A to B and how long it takes.
As an example, let's go back to the process of refraction. Say a plane wavefront between these two rays incident on the interface. After a short time, the Huygens wavelet from this point has reached here, while from this point, let us say in a faster material, this Huygens wavelet has reached here. By the time the right one has reached the interface, the left one has reached here. Then the new wavefront at this time has to be to this tangent.
Which is, of course, the same answer we would get with rays and Snell's law.
But it is in regard to diffraction that we really bless Huygens for the insights he gives us. Diffraction, we remember, is the process by which we hear around corners. If the radio is round the corner of the wall, we cannot see it, but we can still hear it. At one instant, the wavefront is here. At the next, the Huygens wavelets are here, and their envelope is here. The wave is starting to go round the corner. At the next instant, the new Huygens wavelets are here, and their envelope here. Then here, the envelope, and so on. Diffraction. In later modules, we shall apply Huygens to a variety of seismic situations, particularly the fault. But for the moment, let's just carry forward one inference from Huygens, simple but crucial.
We consider the effect of some inhomogeneity in the Earth, a fissure, perhaps, or a dike, or even a local change of velocity. Then between this source and this detector, we can draw a straight ray, unaffected by the inhomogeneity. But it would be quite wrong to think that the actual signal received at the detector is unaffected by the inhomogeneity.
Suppose, as an extreme example, that nothing at all gets through this inhomogeneity, so that there are no Huygens sources on the far side of it. Then the incoming wavefront diffracts around the barrier, yielding a wavefront like this. The wave energy that appears in the shadow zone must come from somewhere. And it can come only from the direct wave. Inevitably, therefore, the amplitude of the wave observed at the detector is reduced by the presence of the barrier. The ongoing wave is strong here, weakened here, and even weaker here.
We are braced then for this conclusion. Propagation of a seismic wave from source to detector involves a large cigar-shaped volume of rock and is affected by any inhomogeneity within that volume. Much affected if the inhomogeneity is central, progressively less outwards.
So the ray is a useful concept for setting up geometry, for travel time equations. But the whole story must involve this cigar-shaped volume of rock around the ray.
Well, there's our whirlwind sketch of the seismic pulse, the generation and propagation of compressional seismic waves in the Earth. But we have to add that compressional waves are not the only waves in the Earth. Surface waves, for example.
Any seismic source makes the surface above it go up and down, thereby generating a spreading circular pattern of surface waves, almost like waves on a pond, but not quite. Because they have low velocity, they are likely to reach the geophones just while we are recording our reflections. Because they are subject to only circular spreading, whereas reflections are subject to spherical spreading, their amplitude is often much greater than the reflections.
So surface waves are our enemies. They are particularly bad if the source is in soft clay, and even worse if the source is shallow, or actually at the surface.
Indeed, the only redeeming feature of surface waves is that they are usually concentrated at low frequency, typically less than about 25 hertz.
So surface waves, yuck. But there is another class of seismic waves that we are beginning to turn to good account. These are the shear waves, basically waves in which the particle motion is not along the ray, but perpendicular to it. We might say S for shake rather than P for push. But for a discussion of those, I have to refer you to the manual. Right here, let's just try to bring it all together. We would like the seismic method to be very, very simple. A spike in, a ray path defined by simple geometry, a spike out, and a simple measurement of travel time. We now know that the reality is much more complex. We lose our simple spike right at the beginning because of the source signature. We lose our simple ray because seismic propagation requires a wide volume of rock. We lose our simple spike again because of absorption. We lose the amplitude of our pulse because of spherical spreading. We lose certainty when surface waves arrive at the same time as reflected waves. And throughout all this, we know we are not measuring enough variables to elicit what the geologist wants to know: depositional environment, rock type, porosity, and so on. All these complications, then, are enemies. To fight them, we must first know them, which is the reason for this module. And then, in later modules, we develop the weapons for this fight. Thus, our weapon to get back to a spike input is source signature deconvolution. Our weapon to get spherical propagation back to rays is migration. To remove spherical divergence, gain expansion. To fight absorption, inverse filtering. To counter surface waves, arrays. And to give us more physical variables, more measurements, the combination of compressional waves with shear waves. Fine. But before all that, we'd better take a look at another fundamental process along the seismic path, the process of reflection. See you in 203.